Module 8, Lecture B, Implementing Strategies. By the end of this lecture, you will be able to configure and run model.fit under a tf.distribute strategy for multi-GPU or multi-worker setups, implement a custom training loop that uses strategy.run and distributed datasets, and troubleshoot common distributed training errors related to shapes, batch sizes, and variable placement. Using fit with strategies. Working with strategy scope. When moving from single device to distributed training in TensorFlow, it is important to understand the strategy scope. This scope is a context where TensorFlow automatically manages models, variables, and optimizers so they can run across multiple devices. By building and compiling your model inside this context, TensorFlow takes care of placing variables and handling communication between devices. This lets you use multiple GPUs or machines without having to manage the distribution details yourself. When using a distribution strategy in TensorFlow, the key decision is which objects you create inside the strategy scope. You should first set up the strategy, enter its scope, and then build your model, optimizer, and any layers or metrics that need to be replicated across devices, such as multiple GPUs. This ensures their variables are correctly mirrored on all devices. After that, you can leave the scope and run training or evaluation as usual, since the scope only affects how objects are created. If you build the model outside the scope, TensorFlow will create non-distributed variables, which can lead to errors or fall back to single device behavior. Using the strategy scope correctly is essential when training models across multiple machines and GPUs. By entering the strategy scope before building your model, TensorFlow can automatically handle how variables are distributed, how gradients are aggregated, and how updates stay consistent. This same boundary also controls how checkpoints are saved, how metrics are combined, and how batch size is interpreted across replicas. Treating the strategy scope as the main container for your model's trainable state helps avoid bugs and makes it easier to scale from a single machine to a large cluster. Python code working with strategy scope. This script demonstrates how to correctly use strategy scope by creating the model within that scope. It focuses on showing the proper placement of model creation, so distributed training works as intended. The training process is kept simple, with only minimal information printed, so the main idea about strategy scope usage remains clear. The comment is instructing you to install TensorFlow version 2.20 if it is not already installed. This step is necessary before running the script because TensorFlow is a required dependency. Ensuring the correct version is present helps the code run smoothly and avoids compatibility issues. We start by importing the operating system module to interact with the system, for example, to work with files or environment variables. We also import the random module so we can generate random numbers and perform random operations, which is useful for tasks like shuffling data or controlling randomness with a seed. Finally, we import the numerical computing library NumPy, which is essential for efficient work with arrays and for performing fast mathematical operations in Python. We begin by importing TensorFlow, a main library used for machine learning and deep learning. Within TensorFlow, we use Keras as a high-level interface that makes it easier to build and train neural networks. We also import the layers module from Keras, which provides essential components like convolutional, pooling, and dense layers. Together, these imports give us the core tools needed to construct and train neural network models efficiently. We set a seed value, such as 42, so that all random operations give the same results every time we run the code. To do this consistently, we set the seed for the random library, for NumPy, and for TensorFlow. Using the same seed across these libraries makes our experiments deterministic, which is important for reproducibility. This consistency helps us debug more easily and reliably compare results between different runs. This line displays the version of TensorFlow that is currently in use. It provides a quick check that the intended version of the library is installed and accessible to the script. Confirming the version helps ensure compatibility with other code or libraries that rely on specific TensorFlow features or behaviors. The code uses TensorFlow to check which physical devices of type GPU are available, so it can see what hardware resources the system has for distributed computation. It then reports how many GPUs it finds. This gives quick feedback on whether the system is suitable for running distributed training workloads. The code first checks how many physical GPUs are available and chooses a training strategy based on that. If more than one GPU is present, it uses a mirrored strategy to distribute training across multiple GPUs and improve efficiency. If there is only one GPU or none, it falls back to a standard single-device strategy. This setup ensures the model automatically makes effective use of whatever hardware resources are available. The code prints the name of the distribution strategy class to show which strategy is currently in use. This lets you confirm whether training is running with a mirrored strategy across multiple graphics processors or with the default strategy on a single device. Knowing this is helpful for debugging and for making sure the distributed training setup is configured as intended. We begin by loading a small portion of the MNIST dataset using Keras. MNIST is a standard dataset of handwritten digit images used to train and test image processing models. In this step, we load only the training data, which consists of images and their corresponding digit labels. The images are stored separately from the labels, so we can easily access each picture and the digit it represents. Using just a subset keeps the data size manageable and suitable for quick demonstrations. To keep this demonstration simple and efficient, the training dataset is reduced to only the first 4,000 samples. Both the input images and their matching labels are limited to this subset. This smaller dataset makes the training process faster and easier to manage while still illustrating how the model works. To prepare the training images for a neural network, each pixel value is converted to a floating point number by dividing by 255, which scales all pixels to a range between 0 and 1 and helps the model train more effectively. After this normalization, an extra dimension is added to the image data to represent the channel. This step is needed because convolutional layers expect inputs that include a channel dimension, even when working with grayscale images, such as those in the MNIST dataset. Before building the model, the code prints the shapes of the training data and labels to confirm they are in the correct format. This check helps ensure that the images and labels match what the model expects as input. By verifying these shapes, you can quickly detect mismatches or errors in the data setup. Catching such issues early makes the modeling process more reliable and efficient. We start by checking the strategy to find how many replicas are training the model at the same time. This tells us how many copies of the model are running in parallel. Then we set the global batch size by taking a base batch size of 128 and multiplying it by either 1 or the number of replicas, whichever is larger. This way, the batch size grows with the number of devices, helping the training process scale efficiently in a distributed setup. We begin by creating a TensorFlow dataset from the training images and labels, so the data can be handled efficiently during training. The dataset is then shuffled with a buffer of 4,000 examples and a fixed random seed to mix the data well and keep the process reproducible. After that, We group the data into batches using the global batch size, which is based on the number of synchronized replicas. This batching step is essential for efficient training, especially when using distributed strategies. This code uses prefetching to speed up the data pipeline by overlapping data loading with model training. With TensorFlow's auto-tune feature, the system automatically chooses how much data to prefetch. As a result, while the model is training on one batch, the next batch is prepared in the background. This reduces idle time and makes the overall training process more efficient. Within the distributed training strategy scope, we define a simple sequential convolutional neural network, so its variables are correctly managed across devices. The model takes grayscale images of size 28 by 28 as input, then applies a convolutional layer with 16 filters and a ReLU activation, followed by max pooling to reduce spatial dimensions. The result is flattened and passed to a dense layer with 32 units and ReLU activation for further feature abstraction. Finally, an output dense layer with 10 units and a softmax activation produces class probabilities suitable for multi-class classification tasks such as digit recognition in the MNIST dataset. The model is now being compiled, meaning it is set up for training. It uses the Atom optimizer with a small learning rate of 0.001, which is a common and effective choice for deep learning. The loss function is sparse categorical cross-entropy, appropriate for multi-class classification when the target labels are integers. Accuracy is chosen as the evaluation metric, so during training we can track how often the model's predictions match the true labels. This line outputs how many replicas are currently synchronized under the chosen strategy. It is used to verify that the strategy is correctly distributing computations across all available devices. By checking this number, you can confirm that variables are being created and updated consistently on every replica. The model is trained using the fit method, which takes the training data as input. Training is run for 2 epochs, so the model goes through the entire dataset twice. The verbose setting is turned off to suppress training logs, keeping the console output minimal and focused only on essential information. To evaluate the model at the end of training, we use the training history object, which stores the values of each tracked metric after every epoch. From this object, we look up the list of loss values and take the final entry to get the last recorded loss. We do the same for accuracy, retrieving its list and selecting the final value. These final loss and accuracy numbers summarize how well the model was performing when training finished. This code reports the model's final loss and accuracy after training. It rounds both values to 4 decimal places to make them easier to read. This creates a clear, concise summary of how well the model performed, so you can quickly inspect and understand the training results. The code prints a message confirming that training finished successfully within the chosen strategy scope. This means the model completed its training without distributed computing errors. It also shows that the strategy for using multiple devices functioned correctly. In short, the printed message verifies that the distributed training setup worked as intended. This script shows how to use TensorFlow's distribution strategies for training a model across available GPUs. It sets a fixed random seed, checks how many GPUs are present, and chooses either a mirrored strategy for multiple GPUs or a default strategy otherwise. The code then loads and normalizes a subset of the MNIST dataset, builds an efficient input pipeline, and defines a simple convolutional neural network inside the chosen strategy scope. The model is compiled with an Atom optimizer and sparse categorical cross-entropy loss, trained for 2 epochs, and finally reports the loss and accuracy. Overall, it confirms that the model can be trained successfully without distribution errors under the selected strategy. Global versus per-replica. When using a distribution strategy, it is important to distinguish between per-replica and global values. A replica is a copy of the model on a single device, such as a GPU, where quantities like loss and gradients are computed separately. So these are per-replica values. Global values are formed by aggregating across all replicas. For example, by taking the mean loss or considering the total batch size. Understanding this difference is essential for correctly interpreting training logs and setting up metrics as you scale your training across multiple devices. When training on multiple devices, the global batch size is the total number of examples processed in one step across all replicas, and this batch is divided among the devices. For example, if the global batch size is 256 and you use 4 GPUs, each GPU handles 64 examples. However, metrics such as loss and accuracy are still computed and reported based on the full global batch. The training strategy combines the results from all replicas into a single global value. So if you do not realize this, you might misunderstand what batch size was used or how quickly the model is converging when comparing different hardware setups. When building input pipelines for distributed training, always distinguish between global batches and per-replica batches. You usually choose a global batch size, and the distribution strategy automatically splits it across devices. So configuring the pipeline directly with per-replica sizes can accidentally create a much larger global batch, which may hurt optimization or exceed memory. Also remember that some quantities, such as gradients, are defined per replica, while others, such as model weights, are shared globally. By consistently checking whether each quantity is per replica or global, you can configure and scale your model correctly across devices. Python code, global versus per-replica. Pause. Global means it's shared across the whole app. Per-replica means each replica gets its own copy. So global is one shared state, and per-replica is one per instance. Got it? This script demonstrates the difference between global values and per-replica values when using TensorFlow distribution strategies. It works with a small dataset to make it easier to see how data is split and processed across multiple devices. By running it in a Colab environment, you can explore how batch behavior changes when computations are distributed. The focus is on understanding how distributed training manages data and operations across replicas. The line with the exclamation mark is a command to install TensorFlow version 2.20.0. It is often used in environments like Google Colab to make sure that this exact version is available. Doing this helps ensure the code runs as expected and remains compatible with the specific TensorFlow features and functions it relies on. We begin by importing several key libraries for our work. The operating system module lets us interact with the system environment, and the random module allows us to generate random numbers, for example when setting seeds for reproducible results. We then import NumPy for efficient numerical operations on arrays and other mathematical tasks. Finally, we bring in TensorFlow, which we will use as the main framework for building and training machine learning and deep learning models. We set a seed value, such as 42, so that all random operations in our code are reproducible. This means that each time we run the program, the random results will be the same. We apply this seed to Python's built-in random number generator, then to NumPy's random generator, and finally to TensorFlow's random generator. Using the same seed across these libraries keeps their random behavior consistent, which makes debugging and verifying results much easier. This line displays the version of TensorFlow that is currently in use. It provides a quick check that your environment is running the expected version of the library. Confirming the version helps ensure compatibility with your code and can be important when diagnosing issues or debugging. The code first checks how many GPU devices are available. If it finds more than one, it uses a mirrored strategy, so training can run synchronously across all GPUs and distribute the workload evenly. If there is only one GPU or none, it falls back to a single device strategy on the CPU. This approach lets the program adapt to the hardware and run efficiently on whatever resources are present. The code checks how many replicas are currently synchronized by querying this information from the selected distribution strategy. This tells us how the workload is being shared across different devices. It then prints the number of synchronized replicas, which reveals the level of parallelism used in the current configuration. We begin by choosing a small global batch size of 8, which is the total number of training samples processed together across all devices. We then compute the batch size for each replica by dividing this global batch size by the number of replicas that run in sync, so each one handles an equal share of the data. To avoid any replica receiving no data, we ensure that this per-replica batch size is at least 1. Finally, we print the global batch size to verify that it is set correctly. The code prints the batch size used by each replica during distributed training. This value is found by dividing the global batch size by the number of replicas working in sync, so each one handles an equal share of the data. Printing this value lets you confirm that the data is evenly split across replicas, which is important for efficient parallel processing. We begin by creating a small synthetic dataset with 32 samples to keep the example manageable. The input features are generated as random numbers arranged in 32 rows and 4 columns, and these values are converted to 32-bit floating point format so they work smoothly with TensorFlow. The labels are created as random binary values, either 0 or 1, for each of the 32 samples, and they are also stored as 32-bit floating point numbers. This setup gives us a simple, compatible dataset of features and labels for demonstrating TensorFlow operations. We first create a TensorFlow dataset from the features and labels using a method that pairs them together into a dataset structure. Then we batch this dataset using the global batch size so the data is grouped into equally sized batches. By enabling the option to drop any leftover data that does not fill a complete batch, we avoid having smaller, inconsistent batches. This setup is important to keep batch sizes consistent across all replicas during distributed training. The code applies the chosen distribution strategy to the dataset, so it can be processed across multiple devices. This setup is important for parallel processing, especially when using multiple GPUs. It ensures that each replica of the model receives the correct portion of the data needed for training. As a result, the workload is split efficiently, and training can be scaled across available hardware. We define a function that builds a sequential neural network model using TensorFlow Keras. It starts with an input layer that takes data with 4 features, followed by a dense layer with 4 units using the ReLU activation to add nonlinearity. The model ends with a dense output layer that has 1 unit and uses the sigmoid activation, which is appropriate for binary classification. The function then returns this model so it can be compiled and trained. Within the strategy scope, we create a new model so it is correctly set up to use the chosen distribution strategy. We then compile this model using stochastic gradient descent with a learning rate of 0.1. The loss function is binary cross-entropy, which matches the binary classification task. We also track accuracy as a metric to monitor how well the model performs during training. This code trains the model for a single epoch using a dataset that is distributed across multiple devices. It calls the model's training function with the distributed dataset as input, so the model sees the entire dataset once. The steps per epoch are set to 2, meaning the epoch is divided into 2 batches. The verbosity is set to 0, so no training logs or progress messages are shown while it runs. After each training epoch, the code reads the global loss and accuracy from the training history to summarize the model's performance. It takes the first recorded loss value, converts it to a floating point number for precision, and prints it. It does the same for the first recorded accuracy value. This quick check provides an overview of how well the model performed during that epoch. We iterate over the distributed dataset just long enough to retrieve a single batch of data. From this batch, we separate the features and the labels, which are spread across the different replicas. We store the features in one variable and the labels in another so we can examine them. After obtaining this first batch, we immediately stop the loop, since we only need that one batch to inspect the shapes of the data on each replica. We inspect the type of the variable that stores data distributed across multiple replicas in TensorFlow to see how the framework manages this data internally. By asking for its type and then reading the class name, we confirm that it is a special object created for handling values spread over different devices. This simple check helps us understand that TensorFlow wraps distributed data in a dedicated structure rather than using a standard data type. This function is used to inspect the shapes of tensors that may be distributed across multiple replicas in TensorFlow. It first checks whether the input is a distributed value. If it is, the function gathers the shape of the tensor on each replica and stores these shapes in a list. It then prints the tensor's name along with the shapes for all replicas. If the tensor is not distributed, it simply prints its single shape and name. This helps us see how data is partitioned across replicas in a distributed setup. We use a helper function to check how the feature and label data are shaped across different replicas in a multi-device setup. It first inspects the features to see if they are distributed, then collects and prints the shape from each replica so we can see how the data is split. We repeat this process for the labels to confirm their distribution matches our expectations. This inspection step is important for verifying that both features and labels are partitioned correctly across devices before training. We use TensorFlow's binary cross-entropy loss to measure how far the model's predicted binary outputs are from the true labels. The loss is configured with no reduction, meaning it is computed separately for each example in a batch, instead of being averaged or summed. This design lets us later examine the loss values for each replica or individual example in more detail. We define a distributed step function optimized with TensorFlow's function decorator to run training efficiently across replicas. Inside it, we create a replica step function that takes input data and labels. This replica step passes the inputs through the model in training mode to produce logits, which are the raw predictions. It then computes the loss for each example by comparing these logits with the true labels using a binary cross-entropy loss object. The replica step returns this per-example loss so we can evaluate the loss for each individual example across all replicas. The strategy runs the replica step function on all replicas at once using the given inputs, so the loss for each example is computed in parallel across the available devices. This produces a separate loss value on each replica. These per-replica losses are then collected and returned so they can be used in later processing steps. We begin by creating a single batch that contains both features and labels, and this batch is distributed across all replicas. We then pass this distributed batch to a training step function that runs on every replica in parallel. During this distributed step, each replica processes its portion of the data and computes the loss for each example it handles. This approach uses the distribution strategy to parallelize training, with each replica independently calculating its own loss. The code examines the shapes of the loss values on each replica before any reduction is applied. It uses a helper function that checks the shapes of distributed values, focusing on the loss computed for each example. By doing this, it reveals how the loss is spread across different replicas and helps you understand how the distribution strategy is behaving. To combine the losses from multiple replicas into one value, we use the strategy's reduce method. We choose the mean as the reduction operation to average the per-replica losses, which are the individual losses from each device. By setting the axis to none, the method reduces across all replicas and returns a single scalar value. This final global loss summarizes the model's overall performance across all devices. This code reports the global mean loss for a single batch. It converts the global loss tensor into a numeric array, computes the average value of that array, and then prints this number. The result is one scalar that represents the average loss across all replicas for that batch. This value helps you assess how well the model is performing during training. This script uses TensorFlow distribution strategies to demonstrate the difference between global and per-replica batch sizes when training a model across multiple devices. It selects an appropriate strategy based on available hardware, computes the number of replicas, and shows how the global batch size is divided into per-replica batch sizes. A synthetic dataset is distributed across devices, and a simple neural network is defined and trained within the strategy scope, reporting global loss and accuracy. The script then inspects the shapes of distributed batches and defines a custom training step that computes per-example loss on each replica. Finally, it reduces these per-replica losses to a single global mean, illustrating how TensorFlow manages data, loss, and computation across multiple devices, while distinguishing between global and per-replica operations. Distributed checkpointing basics. When you move from training on a single device to a distributed setup, checkpointing becomes a coordinated process across all replicas and workers. The goal is still to regularly save the full training state so you can resume after interruptions or roll back to a stable point. In distributed training, this full state includes model parameters, optimizer states, learning rate schedules, and other trackable components. The distribution strategy manages how these pieces are synchronized and aggregated across devices, so saving and restoring checkpoints works much like in non-distributed runs, even though it operates over multiple GPUs or machines. In distributed checkpointing, you save the logical state of the model rather than device-specific copies of the data. Even if variables are mirrored across multiple GPUs, the checkpoint stores only one authoritative value for each variable, ensuring consistent replicas when saving and restoring. In multi-worker setups, this approach hides the details of the physical hardware layout, so you can change the number of GPUs or move to a different cluster as long as the model's logical structure stays the same. This abstraction makes checkpoints portable artifacts that can move smoothly between different environments. In distributed training, effective checkpointing means choosing appropriate save intervals and making sure only the designated worker writes checkpoints to storage. Long-running jobs on shared clusters benefit from more frequent checkpoints to guard against interruptions, while shorter runs may only save at key points, like the end of an epoch. Checkpointing is often combined with evaluation and deployment, for example, by validating each checkpoint and archiving the best model for later use. Because device placement is abstracted away, These checkpoints can be reliably loaded on different clusters and hardware setups, keeping training pipelines robust, scalable, and reproducible. Python code, distributed checkpointing basics. This script introduces the basics of distributed checkpointing. It demonstrates how to use a mirrored strategy together with the standard model training function in a safe way. The focus is on keeping the behavior simple and the output short. It is designed to be accessible and beginner-friendly while still showing the core idea of distributed checkpointing. The line that begins with an exclamation mark is a command to install TensorFlow version 2.20.0. It is used to make sure the code runs with this exact version of the library. This can be important for compatibility with specific features or functions used later in the script. Such a command is typically executed in a Jupyter notebook or a similar environment that allows direct use of shell commands. We begin by importing a few key tools for our project. The operating system module lets us work with the file system, and the pathlib module gives us a convenient way to handle file paths. We also import the numerical library NumPy to generate random data. Finally, we bring in TensorFlow, which we will use to build and train our machine learning model. We begin by setting fixed random seeds for both NumPy and TensorFlow so that any random operations give the same results every time the code runs. This step is important for reproducibility because it makes our experiments consistent and easier to compare. By aligning the random number generation in these two libraries, we ensure that repeated runs of the same experiment behave in a predictable and reliable way. This line of code displays the version of TensorFlow currently in use. It provides a quick check that the intended version is installed and running. Confirming the version helps ensure that the rest of the code is compatible and behaves as expected. The code first uses a TensorFlow configuration call to check whether any GPU devices are available on the system. This step identifies if there are GPUs that can be used for distributed computing. It then prints how many GPUs were found, giving a quick summary of the hardware resources that might be used to speed up the workload. The code first checks how many physical GPUs are available. If there is more than one, it uses a TensorFlow MirroredStrategy to distribute computations across all GPUs, allowing training to run in parallel. If there is only one GPU or none, it falls back to the standard non-distributed strategy. This setup lets the model automatically adapt to the available hardware and use it as efficiently as possible. The code prints the name of the distributed training strategy class being used. By showing the class name of the strategy object, it lets you check whether MirroredStrategy or a default strategy is active. This confirms how the model will be distributed across available resources and helps you understand the training setup. In short, it is a quick way to verify which distribution strategy is in effect. We start by setting up a main directory using a path handling library that works across different operating systems. The script then creates this directory if it does not already exist, so it can run safely without errors. Inside this main directory, we define a checkpoints folder where model checkpoints will be saved during training. This folder is also created if needed, ensuring the file system is ready for storing model states. We are creating a small synthetic dataset for a classification task. It will contain 256 total data points, and each data point will be described by 20 features. The classification problem will involve 3 different classes, so each data point will be assigned to one of these 3 categories. To create a simple synthetic dataset for classification, we first use a random number generator to produce a two-dimensional array of feature values, with one row per sample and one column per feature, and convert it to a float32 type so it works smoothly with TensorFlow. We then generate random integer labels, using the number of classes as the upper limit, so that each sample gets one class label. These labels are stored in a one-dimensional array and converted to an int32 type. Together, these random features and labels form a basic dataset that can be used to test classification models. We start by checking that the number of feature samples matches the number of labels, so every input has a corresponding target, which is essential for supervised learning. We also verify that each sample contains the expected number of features. Together, these checks ensure the data is correctly structured before we build and use the dataset. We begin by choosing a batch size of 32, which controls how many training samples are processed together at once. Then, we build a TensorFlow dataset from our features and labels, using a method that slices them into matching pairs. This pairing organizes the data so it can be fed efficiently into the training pipeline. As a result, the model can process groups of examples in a structured and optimized way during learning. The dataset is shuffled using a buffer as large as the dataset itself so that the samples are thoroughly mixed. A fixed random seed is used, so this shuffling is deterministic and produces the same order every time, which supports reproducible experiments. After shuffling, the data is split into batches of a chosen size, so the model can train on smaller, manageable groups of samples at a time. Within the chosen distribution strategy, we build a simple sequential neural network so its operations follow that strategy. The model begins with an input layer that matches the predefined number of features. It then uses a dense layer with 16 units and a ReLU activation to introduce nonlinearity. Finally, it adds a dense output layer with as many units as there are classes, using a softmax activation to produce class probability predictions. Within the strategy scope, the model is compiled by assigning an optimizer, a loss function, and a performance metric. It uses the Atom optimizer with a learning rate of 0.01 to update the model's weights during training. The loss function is sparse categorical cross-entropy, which is appropriate for multi-class classification when the labels are given as integers. Accuracy is also tracked as a metric to monitor how well the model is performing while it trains. We define a path for saving model checkpoints that includes both the directory and a file naming pattern based on the epoch number. Then we create a checkpoint callback using the TensorFlow model checkpoint feature, configured to save the entire model at the end of every epoch. It tracks the loss metric, but does not restrict saving to only the best performing model, so a new checkpoint is written after each epoch, regardless of performance. The verbosity is set so that no messages are printed during the saving process. We train the model using the keras-fit method, which runs on the model and uses our prepared dataset as input. The training is set to run for 2 epochs, meaning the model processes the entire dataset twice. The verbose setting is turned off so it does not print progress during training. We also provide a list of callbacks that includes a checkpoint callback, which saves the model at the end of each epoch so we can restore it later if needed. The code first collects all saved checkpoint files in the checkpoint directory that use the keras format, then sorts them, typically by the epoch number in their names. It prints a message confirming that checkpoint files have been saved, and then goes through each file, printing its name. This produces an ordered list of all saved checkpoints, making it easy to verify that the model's state was correctly saved at each training epoch. Within the strategy scope, we create a new model and load the most recent checkpoint into it using TensorFlow's model loading function. This restores the model's structure, learned weights, and optimizer state from the saved file. As a result, we can resume training or run evaluation as if the training process had never been stopped. To compare the original and restored models, we first take a single batch of features and labels from the dataset. We then evaluate the original model on this batch and record the results without printing them. Next, we run the restored model on the same batch in the same silent way. By comparing these two sets of results, we can confirm that the restored model behaves the same as the original on this sample of data. We print a brief comparison of the evaluation results for the original model and the restored model to confirm they behave the same. By checking that their loss and accuracy values match, we can see whether the restored model maintains the original performance. This quick comparison serves as a simple validation that the checkpointing and restoration process worked correctly. This script shows how to use TensorFlow's MirroredStrategy to perform distributed checkpointing. It sets deterministic seeds, checks for available GPUs, and creates a small synthetic dataset of random features and labels. Within the strategy scope, it defines and compiles a simple neural network, then trains it for a couple of epochs while saving checkpoints at each epoch. After training, it lists the saved checkpoints, loads the latest one into a new model, and evaluates both the original and restored models on the same batch. The similar loss and accuracy values confirm that checkpointing and restoration work correctly in this distributed setup. Custom distributed loops. Writing strategy run steps. When moving from a high-level training interface to a custom distributed training loop, the key piece to understand is the step function. This function runs on each device, takes a portion of the global batch, performs the forward pass, computes the loss, and applies gradients to update the model. Training is organized as a sequence of these steps, which can run in parallel across multiple GPUs. The distribution strategy takes care of calling the step function on each replica, but you are responsible for defining what happens inside it, including how inputs are handled, how loss is calculated, and how updates are applied. For example, in a vision task, each replica processes different images, computes its own loss, and contributes gradients to update the shared model weights. When designing a step function for distributed training, decide which work is repeated on each replica and which state is shared. The step function typically gathers features and labels, runs the forward pass, computes the loss for each replica, and then participates in cross-replica reduction before applying gradients. Model variables and optimizer states are created once and shared so that all replicas update the same parameters consistently. In natural language processing, for example, different replicas may process different batches of sentences, compute their own losses, and then synchronize updates to keep embeddings and weights aligned across devices. When running this step function in parallel on multiple devices, it must be efficient and free of side effects that break synchronization. Random operations such as data augmentation should be handled carefully so replicas do not diverge, and logging or metrics should be tracked separately on each device. Loss values need to be scaled and normalized consistently so that, when combined, they behave like a single device run with the same effective batch size, since inconsistent normalization can cause unstable training in applications like recommendation systems. By designing the step function to be aware of these side effects, you allow the distribution strategy to coordinate parallel execution correctly across all hardware. Python code. Writing strategy run steps. This script demonstrates a basic step in distributed training. It highlights how to use the strategy run operation together with a custom training step. The goal is to help you understand how replica step functions work in a distributed setting. By studying this example, you can see how a single training step is executed across multiple replicas. The line with the exclamation mark and the pip install command is a shell command that installs TensorFlow version 2.20.0. Using this specific version helps ensure the script runs correctly and remains compatible with the rest of the code. The exclamation mark shows that the command is intended to be executed from within a Jupyter notebook or a similar environment that allows running shell commands directly. We begin by importing TensorFlow, the main library we will use to build and train machine learning models. TensorFlow provides tools for creating neural networks, managing data, and running computations efficiently. It also supports distributed training, which is the primary focus of this script. In short, importing TensorFlow sets up everything we need for model construction and large-scale training. The code sets a fixed seed for TensorFlow's random number generator so that its random values are the same every time you run the script. This makes the results deterministic and repeatable. Having reproducible results is important for debugging and for reliably comparing outcomes across different runs of the program. The code uses TensorFlow's configuration tools to list all physical devices of type GPU, which reveals whether the system has graphics processors available for computation. Knowing if GPUs are present is important because it affects how you choose a distribution strategy for training models. In short, this check helps you decide the best way to run and scale your training process based on the available hardware. The code first checks whether any physical GPUs are available. If it finds GPUs, it uses TensorFlow's MirroredStrategy to distribute computation across them for parallel processing and faster training. If no GPUs are detected, it falls back to a single device strategy that runs on the CPU. This approach lets the same code adapt to the available hardware and run efficiently on both multi-GPU systems and CPU-only environments. This line displays the TensorFlow version in use and the type of distribution strategy that has been selected. It helps you verify that the correct TensorFlow version is installed. It also confirms that the intended distribution strategy, such as a mirrored strategy or a single device strategy, is properly set up for spreading computations across devices. We begin by creating a small synthetic dataset to use as example input for a model. To do this, we generate random numbers from a normal distribution and arrange them into a tensor with 64 rows and 4 columns. This tensor serves as our feature data, standing in for real input examples. Using a normal distribution helps the synthetic data resemble typical patterns found in real-world datasets, making the demonstration more realistic for training. We create labels for our dataset by summing the feature values along the second axis, so each data point is reduced to a single numeric label. In other words, for every example, we add up all its feature values to produce one output value. We keep the result in a two-dimensional shape to match what the model expects, which is why we preserve the original dimensions when performing this sum. We create a TensorFlow dataset from our feature and label tensors to prepare the data for model training. Using the Dataset API lets us manage and process data efficiently, especially for large or distributed workloads. It supports important operations like batching and shuffling, which help the model train more effectively. Overall, this setup provides a smooth and scalable data pipeline for feeding data into the training process. The code groups the dataset into batches of 8 samples to make training more efficient by processing several examples at once and better using the hardware. It is set to drop any leftover samples that do not form a complete batch, so only full batches are used. This keeps the batch size consistent, which is especially important when training is distributed across multiple devices. The code uses the chosen distribution strategy to split the base dataset for parallel processing across available hardware, such as multiple GPUs or CPUs. This distribution ensures that each model replica receives its own portion of the data. As a result, training can run efficiently and in sync across all devices involved. In this setup, the global batch size is defined as 8, and this value is important for correctly scaling the loss during distributed training. By using a global batch size, the loss is computed in a consistent way across all replicas, no matter how many are used. This consistency helps preserve the accuracy and stability of the model's training behavior. Within the strategy scope, we build a simple Keras sequential model with 2 dense layers. The first layer has 8 units with a ReLU activation and takes inputs with 4 features. And the second layer is a single unit output layer suitable for regression. Defining the model inside the strategy scope ensures that variable creation and related operations are automatically distributed across available devices. This setup enables efficient parallel training of the model. We use a simple optimizer called stochastic gradient descent to update the model's weights during training. It adjusts the weights step by step to reduce the loss function. The learning rate is set to 0.05, which controls how large each update step is. Choosing this optimizer and learning rate is important for effectively improving the model's performance over time. We create a mean squared error loss object using TensorFlow to measure the difference between predicted and actual values. By configuring it so that the reduction is set to none, the loss is computed separately for each example, instead of being averaged over the whole batch. This setup lets us control how the individual losses are scaled or combined later in the training process. We define a function called compute loss that calculates the loss for each replica during distributed training. Inside this function, we first compute the unscaled loss for every example in the batch using a mean squared error loss object. This produces one loss value per example, which serves as the basis for later computing a scaled loss that takes the global batch size into account. This part of the code scales the loss by the global batch size to keep training correct. It uses TensorFlow's function for computing average loss, which takes the loss for each example and divides it by the global batch size, here set to 8. This scaling is especially important in distributed training because it ensures the loss is averaged consistently across all replicas. As a result, the training process remains stable and comparable no matter how many replicas are used. We define a training step function and decorate it with TensorFlow's function optimization to make it run efficiently. This function performs a single training step in each replica in a distributed setup. Within the function, we unpack the distributed inputs into separate features and labels. This unpacking prepares the data so it can be processed correctly during the training step. We use TensorFlow's gradient tape to record the operations in our model, so we can automatically compute gradients later. Within this recording context, we run a forward pass using the distributed input features. The model is placed in training mode so that layers that behave differently during training, such as dropout, are applied correctly. This forward pass produces predictions from the input data that will later be used for learning. The code computes a loss value for each replica by calling a loss function with the distributed labels and the model's predictions. This function returns a loss that is then scaled by the global batch size. Scaling by the global batch size ensures that the loss reflects the combined effect of all replicas. This adjustment is essential for keeping training behavior consistent when using distributed strategies. This code uses TensorFlow's gradient tape to compute how the loss changes with respect to each trainable variable in the model. Gradient tape records the operations during the forward pass. Then its gradient method calculates the contribution of each variable to the loss. These gradients are then used to update the model's weights, which is a key step in the training process. This step uses the optimizer to apply the computed gradients and update the model's weights. The optimizer takes each gradient together with its corresponding model parameter and adjusts that parameter. By changing the weights according to the loss, the model gradually improves its performance on the data. This update process is what allows the model to learn. The function calculates a loss value for each replica during training. These individual losses are then combined and reduced across all replicas. This aggregation produces a single overall loss that guides how the model's weights are updated. By using the combined loss from all replicas, the training process can more effectively adjust the model. We define a function to perform the distributed training step and decorate it with TensorFlow's optimization feature for faster execution. Inside this function, we call the strategy.run method to execute the training step in parallel on each replica. We pass the distributed inputs into this method, so the model can process data across multiple devices at the same time. This approach fully leverages distributed computing by ensuring that every replica actively contributes to training. The code combines the loss values from all replicas into one scalar loss. It does this by calling the strategy's reduce method, which aggregates the per-replica losses. The chosen reduction is a sum, so it adds all replica losses together. The result is a single loss value that represents the total loss for the distributed training step. We train the model for several passes over the dataset, in this case 3 epochs, so it can learn from the data multiple times. At the start of each epoch, we set a running loss value to 0. As training progresses through that epoch, this value accumulates the total loss. Resetting it each time ensures the loss we track belongs only to the current epoch, which then allows us to compute and compare the average loss across epochs. We start by setting a counter for the number of batches to 0. This counter tracks how many batches are processed during each training epoch. At the end of the epoch, we use it to compute the mean loss by dividing the total loss by the number of batches. This ensures we get an accurate average loss for that epoch. During distributed training, we loop over each batch in the dataset and call a distributed training step for each one. This step runs the training logic in parallel on all replicas, with each replica handling part of the batch. The computation then combines to produce a single loss value for that batch. This loss is used to evaluate how well the model is performing at that point in training. The code adds the loss from each batch to a running total for the current epoch and increases a batch counter by 1 each time. By the end of the epoch, this running total and the number of processed batches can be used to compute the average loss. This process is essential for tracking how the model is performing over the entire epoch. To find the mean loss for an epoch, we divide the total loss accumulated during that epoch by the number of batches. We use TensorFlow's cast operation, so the batch count is treated as a floating point value. This ensures the division is done with proper numerical precision and the resulting mean loss is accurate. The code prints a short summary after each training epoch, showing the epoch number and the average loss for that epoch. This summary gives a quick snapshot of how training is progressing. By watching how the mean loss changes over time, you can monitor how well the model is learning. We loop over the distributed training dataset one batch at a time, and for each batch, call the distributed training step function, which runs the training logic across all available devices. After processing the first batch, we intentionally stop the loop so we can inspect the resulting tensor shapes and the loss value. This check helps confirm that the distributed setup is working correctly. The final loss from that batch is saved in a variable for later inspection or logging. The code reports the final loss value after a distributed training step, giving a concrete measure of how well the model has learned from the data. This printed loss helps you verify that the training process is behaving as expected. Converting the loss to a floating point number makes the output clearer and easier to interpret. This script shows a basic example of distributed training in TensorFlow. It sets a fixed random seed, checks for GPUs, and either uses a mirrored strategy for multiple devices or falls back to a single CPU. It builds a simple synthetic dataset, defines a small sequential model with a dense layer and an output layer, and configures an optimizer with mean squared error loss. A training step function computes the loss, applies gradients to update the model weights, and is run in parallel across replicas using the chosen strategy. The script trains for several epochs while printing the mean loss, then runs one final distributed step to inspect the last loss value, illustrating how TensorFlow's distribution strategies manage parallel training. Building distributed datasets. When moving from single device to distributed training, you must rethink how you build your dataset so it works across multiple replicas. Instead of viewing a batch as data for one model, treat it as a global batch that is split into slices, with each replica processing its own portion. This changes how you choose batch size, shuffle data, and assign examples so replicas do not overlap. For example, a global batch of 128 images on 4 GPUs becomes 4 batches of 32, all produced by a consistent and deterministic data pipeline. Structuring your dataset this way is key to stable and efficient distributed training. When preparing data for distributed training, you build a single dataset pipeline that the distribution strategy can automatically split across devices. You first create a dataset of individual examples, then apply operations such as shuffling, repeating, and batching so that the final dataset represents the full global batch. The strategy then divides this global batch into per-replica batches for each device, which keeps the pipeline simple while still using parallelism. For example, when training a language model on large text corpora, the dataset can read from many files, process the text, and form large global batches so each worker receives a balanced and diverse portion of the data. In multi-worker training, each worker must process a different part of the dataset so the system scales efficiently and does not repeat work. This is usually handled by automatic sharding in the distribution framework, which splits data by files or indices so different workers see different data. The data is then shuffled, batched into global batches, and divided across devices such as GPUs. By carefully managing sharding, shuffling, and batching, you build a strong input pipeline that improves convergence speed, hardware utilization, and training reliability at different scales. Python code, building distributed datasets. This script introduces the basics of working with distributed datasets. It uses a simple example with TensorFlow's distribution strategy to show how data is handled across multiple devices. The main idea is to understand the difference between the global batch, which covers all devices, and the per-replica batch, which is the portion of data each device processes. The line with the exclamation mark is a command that installs TensorFlow version 2.20.0. Using this exact version makes sure the script runs with the expected features and behavior. It helps keep dependencies consistent and prevents problems that could occur if a different TensorFlow version were used. To begin setting up TensorFlow training, we import a few key Python modules. We use the operating system module to interact with system settings, and the random module to generate random numbers for reproducible experiments. We also import NumPy for efficient numerical work with arrays and mathematical operations. Finally, we bring in TensorFlow itself, which provides the main tools for building and training our machine learning models. We set a seed value, such as 42, to make all random operations reproducible. This means that each time we run the code, the random results will be the same. We apply this seed to the random module, to the NumPy random number generator, and to TensorFlow's random number generator. Doing so ensures consistent behavior in tasks like initializing neural network weights, which is important for debugging and comparing results across different runs. This line displays the version of TensorFlow that is currently in use. Knowing the exact version helps you check compatibility with your code and libraries. It is also useful for debugging, since different TensorFlow versions can change features or behavior. By printing the version, you can quickly confirm that your environment matches what your project requires. The code first checks how many GPU devices are available. If it finds more than one, it uses a mirrored strategy, so the model can train in parallel across multiple GPUs. If there is only one GPU, or none at all, it falls back to a single device strategy on the CPU. This approach lets the same code run on different hardware setups, while making the best use of whatever resources are present. This code prints the name of the distribution strategy currently in use by reading the class name of the strategy object. Doing so lets you confirm that the correct strategy has been selected for your hardware setup. It is mainly used for debugging and for checking that the program is running with the intended configuration on the right devices. To build a simple synthetic dataset, we first choose how many examples it will contain, such as 32 data points. We then set the feature dimension to 4, so each data point has 4 features. Finally, we define 3 classes, meaning the data will be grouped into 3 distinct categories for classification. These basic parameters create a controlled setup for testing and training a model. We create a simple synthetic dataset by first generating numeric feature values from a normal distribution, arranged in an array whose size is determined by the number of examples and the feature dimension. This array is then converted to a 32-bit floating point type, so it works smoothly with TensorFlow. Next, we generate integer labels by drawing random values between 0 and the number of classes, with one label for each example. Together, these feature and label arrays form a basic dataset suitable for training models. The code uses TensorFlow's data tools to wrap the feature and label arrays into a single dataset object. This step prepares the raw arrays so they can be fed efficiently into machine learning models. By turning the arrays into a dataset, TensorFlow can handle and manipulate the data more effectively during training. This makes the training process smoother and more scalable. In this setup, the global batch size for training is set to 8, meaning each training step processes 8 examples at a time. Batch size is important because it influences memory usage and how quickly the model converges. Smaller batches lead to more frequent updates to the model's weights, while larger batches can be more computationally efficient but update less often. We begin by shuffling the base dataset so that all examples are randomly rearranged, using the full dataset size as the buffer to ensure thorough mixing before training. Then we set the dataset to repeat once, meaning it will be used for exactly one full pass and then stop, which helps control the number of training iterations. Finally, we group the data into batches of 8 examples, creating smaller, manageable chunks that can be processed efficiently in parallel during training. To verify that dataset batches are formed correctly, we take a single batch from the training data and inspect it. We iterate over the dataset, extract one batch of features and labels, and then check the shape of the feature batch. This shape should match the expected global batch size. Confirming this ensures that the data preparation process is working properly before we move on to training the model. We use the strategy's experimental distribution method to create a distributed dataset from the global dataset. This allows the data to be split and processed across multiple devices, such as GPUs or CPUs, according to the chosen distribution strategy. By dividing and managing the data in this way, we enable parallel processing, which is essential for efficient training in a distributed environment. We define a function that builds a TensorFlow Keras sequential model. It begins with an input layer that matches the feature dimension of the data. Then it adds a dense layer with 8 units and a ReLU activation to introduce nonlinearity. Finally, it adds a dense output layer with as many units as there are classes, producing raw prediction scores for each class, and returns this complete model. Within the distribution strategy scope, we first build a simple sequential model so it is correctly set up for distributed training. We then create an optimizer using stochastic gradient descent with a learning rate of 0.1 to update the model's weights. Next, we define the loss function as sparse categorical cross-entropy, which is appropriate for classification problems with integer labels. We also indicate that the outputs are raw logits, not yet passed through a softmax, and we disable automatic reduction so we can handle how the loss is combined across different replicas ourselves. We define a function that computes the loss for each training example using a sparse categorical cross-entropy loss object. This function first calculates an individual loss value for every example in the batch. It then uses a TensorFlow utility to average these values across the entire global batch. By doing so, the loss is correctly scaled for distributed training, ensuring that the overall loss reflects all examples processed in parallel. The training step function is wrapped with TensorFlow's function decorator, so it is compiled into an efficient computation graph. Inside it, a nested replica step function handles the inputs for each replica by splitting them into features and labels. Within a gradient tape context, the model uses the features to produce predictions, and a separate loss function computes the loss from these predictions and the labels. Gradients of this loss, with respect to the model's trainable variables, are then calculated and applied using the optimizer to update the model's weights. The loss value for that replica is finally returned. The code first uses the distributed training strategy to run the replica step function on all available replicas in parallel, using the provided distributed inputs. Each replica computes its own loss, and then the strategy's reduce operation aggregates these losses into a single value. This reduction sums the per-replica losses and converts them into a mean loss, ensuring the overall loss is computed consistently across devices. The function then returns this mean loss as a single scalar that represents the average loss across all replicas for the current training step. We begin by setting a counter to 0 to track how many training iterations have been run. Then we loop over each batch in the distributed training dataset, increasing the counter by 1 for each batch. For every batch, we call the training step function, which computes the loss for that batch and updates the model's weights. The loss returned by this function is stored, and we print the current iteration number along with its loss value to monitor training progress. The final line of the script prints a confirmation message that the custom distributed training loop has finished successfully. This indicates that the training process ran to completion without errors. It also reassures us that there were no issues with data shapes or other problems. Overall, it confirms that the distributed dataset and model training behaved as intended. This script shows how to build and train a distributed dataset in TensorFlow. It sets a fixed random seed, selects an appropriate distribution strategy based on available hardware, and creates a small synthetic dataset of numeric features and integer labels wrapped in a TensorFlow dataset. The data is shuffled, repeated once, batched globally, and checked to ensure the batch shapes are correct. A simple sequential model with 2 dense layers is defined and trained inside the chosen strategy using sparse categorical cross-entropy loss and stochastic gradient descent. A custom training loop runs a training step on each replica, averages the per-example loss across replicas, and prints the loss at each step, confirming that distributed training runs correctly without shape problems. Replica metrics reduction. When you move from training on a single device to a distributed setup, each GPU or worker first computes its own loss and metrics, such as accuracy, on its share of the batch. These per-replica values are then combined or reduced into a single result that represents the behavior of the whole system. This reduction step is important because it affects how you interpret training progress and compare different hardware configurations. Without a consistent and correct reduction strategy, differences in loss across replicas can lead you to misread your logs and dashboards. Proper replica metric reduction ensures that the reported performance truly reflects how the model is training overall. In a custom distributed training loop, each replica computes its own metrics, such as loss, on its local data. After this step, you collect one value per metric from each replica, and then reduce them to a single value per metric, usually by averaging or summing. The choice between mean and sum depends on the metric. For normalized losses, averaging keeps the interpretation as loss per example, while for count-based metrics, summing is more appropriate. For example, in a recommendation system, you would sum the number of correct clicks across replicas, but average the loss per user based on the data each replica processed. When you scale training across more GPUs or workers, you must handle how you combine metrics from each replica carefully to keep optimization stable and monitoring accurate. If you increase the number of replicas but still use a summed loss instead of a mean, the reported values can change even when the model's true performance does not. Your metric reduction should match the effective batch size, so learning rates and regularization behave as intended. In large, multi-server setups, consistent reduction is essential for trustworthy alerts and dashboards. Ensuring that the metrics you see truly reflect the overall behavior of the system and support sound decisions and debugging. Python code, replica metrics reduction. This script demonstrates how to reduce and aggregate metrics across replicas in a simple way. It uses a TensorFlow distribution strategy together with a very small dataset. The main emphasis is on showing how to write a custom training loop and how to correctly combine metric values from multiple replicas into a single result. The line that begins with an exclamation mark is a shell command that installs TensorFlow version 2.20.0. It is typically run in a Jupyter notebook or similar environment. The purpose is to make sure that this exact TensorFlow version is available, so the script can run correctly. This helps maintain compatibility with the rest of the code, which depends on features and behavior specific to that version. We begin by importing 3 key libraries. The operating system library lets our program interact with the computer's operating system. The random library gives us tools to generate random numbers and make random choices. Finally, we import NumPy, a numerical computing library that helps us work efficiently with arrays and perform mathematical operations. We begin by importing TensorFlow so we can use its tools to build and train machine learning models. After that, we check which version of TensorFlow is installed. Knowing the version is important because different versions can have different features or behaviors. This helps us make sure our code is compatible and works as expected. We set a seed value of 42 so that our random results are reproducible, meaning we get the same random numbers every time we run the code. We first set the seed for Python's built-in random number generator, then for NumPy's generator, and finally for TensorFlow's generator. This makes all random behavior, such as generating numbers or initializing model weights, consistent across runs. Having reproducible randomness is important for debugging and for fairly comparing results between different executions of the code. This line displays the version of TensorFlow currently in use. It lets you quickly verify that the correct version of the library is installed and running. Confirming the version helps ensure your code is compatible with the library and that the expected features are available. The code first checks whether any GPUs are available using TensorFlow's configuration tools. If GPUs are found, it uses a MirroredStrategy to split the data and run training in parallel across multiple GPUs, which can speed up computation. If no GPUs are available, it falls back to a single device strategy that runs on the CPU. This approach lets the same code adapt to the hardware it is running on and work correctly on any machine. We create a small synthetic dataset to test a classification model by choosing 64 samples, each with 8 features, and assigning them to 3 possible classes. This means we have 64 data points. Every point is described by 8 attributes, and the model must distinguish among 3 categories. Using this compact setup makes it easier to test and validate the model's performance on a manageable scale. To simulate data for a classification model, we first create random input features using a normal distribution, forming an array with the desired number of samples and features, and store it in a standard floating point format. Then we generate random integer labels that represent class IDs, making sure there are as many labels as samples, and that they span the chosen number of classes. Together, these random features and labels form a synthetic dataset that can be used to test or demonstrate classification methods. Before creating the dataset, the code verifies that the number of feature samples matches the number of labels. This check ensures that every set of input features has a corresponding label. Having this one-to-one match is essential for training the model properly and avoiding errors during learning. We begin by choosing a batch size of 16, which controls how many samples are processed together at once during training. Then we build a TensorFlow dataset from our feature and label arrays. This dataset structure lets us handle the training data efficiently and iterate over it in an organized way throughout the training process. The dataset is first shuffled using the total number of samples and a fixed random seed so that the order is both randomized and reproducible. This prevents the model from picking up patterns based on the original order of the data. After shuffling, the data is split into batches of a chosen size, which makes training more efficient and lets the model process the data in manageable chunks. The code uses a chosen strategy to spread the dataset across multiple devices so the data can be processed in parallel. Each replica handles a different portion of the data, which makes better use of the available hardware. This distributed setup is crucial for training on large datasets or when using multiple GPUs. Overall, it enables the training process to scale and improves performance. Within the strategy scope, we build a simple Keras sequential model with an input layer that matches the number of features in the data. We then add a dense layer with 16 units and a ReLU activation to introduce nonlinearity. After that, we include a final dense layer with as many units as there are classes, which produces raw prediction scores for each class. This model design can be trained in a distributed way across multiple devices when available. Within the strategy scope, we set up a loss function using TensorFlow's sparse categorical cross-entropy, configured so it does not automatically combine losses across the batch. This lets us control how the batch loss is handled later in the training process. We also create an atom optimizer with a learning rate of 0.01, which updates the model's weights during training to reduce this loss. This function computes the loss for each replica during distributed training. It first uses a sparse categorical cross-entropy loss to compare the predicted class probabilities with the true class labels for each example. Then it averages these individual losses over the entire global batch. This averaging ensures that the loss is consistent across all replicas, so that gradient updates remain correct and comparable in the distributed setting. The training step function, optimized with TensorFlow's function decorator, defines a replica step that runs on each replica to process a batch of features and labels. Within this step, a gradient tape tracks operations as the model converts features into logits, and a separate loss function computes the per-example loss. The code then finds the predicted class by taking the index of the largest logit, compares these predictions to the true labels to determine which are correct, and sums them to get the number of correct classifications. Finally, it computes gradients of the loss with respect to the model's trainable variables, applies these gradients using the optimizer to update the model, and returns both the loss and the count of correct predictions. The code uses the strategy's run method to execute a replica step function on all available replicas at the same time. This method takes the replica step function and the distributed inputs, then applies the functions separately on each replica. During this parallel execution, each replica computes its own loss and number of correct predictions for its portion of the batch. These per-replica results are then returned so they can be aggregated later. We use the strategy's reduce operation to combine metrics across all replicas in distributed training. First, we compute the average loss by reducing the per-replica loss values to a single mean. Then, we reduce the per-replica counts of correct predictions by summing them to get the total number of correct results. Finally, we return this mean loss and total correct count as consolidated metrics for the entire distributed setup. We set the number of training epochs to 1, meaning we will pass through the dataset a single time. At the start of this epoch, we initialize values to track the total loss and the number of correct predictions, both starting at 0. We also set a counter for how many batches we process. This setup allows us to accumulate and monitor these metrics as we iterate over the dataset during training. During training with a distributed dataset, we process each batch by calling the training step function with that batch. This function returns the mean loss and the number of correct predictions for the batch. We convert these results to NumPy values and add them to running totals for loss and correct predictions across the entire epoch. We also count how many batches have been processed, so we can later compute the average loss and accuracy for the epoch. To evaluate the model for an epoch, we first find the average loss by dividing the total loss by the number of batches, which summarizes performance across all batches. We then compute how many examples were processed by multiplying the number of batches by the batch size. Using this total number of examples, we calculate accuracy as the number of correct predictions divided by the total examples. Together, the average loss and accuracy show how well the model is performing on the classification task. The code prints the final, reduced metrics collected from all replicas at the end of an epoch. It first converts the average loss to a floating point number and prints it, showing how well the model is minimizing the loss function overall. It then does the same for accuracy, printing the reduced accuracy as a floating point number. This accuracy value represents the fraction of correctly classified examples and summarizes the model's classification performance across all replicas. This script shows how to run distributed training in TensorFlow using the Strategy API with a focus on combining metrics from multiple replicas. It sets up a reproducible environment, chooses a distribution strategy based on available GPUs, and builds a small synthetic classification dataset. Inside the strategy scope, it defines a simple neural network, a sparse categorical cross-entropy loss, and an atom optimizer. A custom training loop then processes each batch across replicas, computes loss and accuracy on each replica, and uses TensorFlow reduction operations to produce a mean loss and total correct predictions. After one training epoch, the script reports the overall mean loss and accuracy, illustrating how to manage distributed training and aggregate metrics across devices. Distributed debugging essentials. Replica shape mismatches. When scaling a model across multiple devices, a common problem is that the replicas do not see tensors with matching shapes. Each device processes a portion of the global batch, so their inputs, labels, and activations must all have the same dimensions. If batch sizes are uneven or padding is inconsistent, one device may receive more or fewer examples than another. This mismatch leads to shape errors when combining results, such as during gradient aggregation. When you see replica shape mismatches in distributed training, focus on how the global batch size is split across devices and how your input pipeline handles the end of the dataset. For example, with 4 GPUs and a global batch size of 64, each GPU expects 16 examples. So if the dataset size is not a multiple of 64, the final batch may be smaller and cause shape errors when outputs are combined. To avoid this, configure the pipeline to drop leftover data, or otherwise ensure that every replica always receives the same batch shape. In addition, when working with data like medical images from different sources, standardize all inputs to the same shape before distributed execution to prevent similar errors. Replica shape mismatches happen when conditional logic behaves differently on different devices, causing tensors to have different shapes. For instance, if a mask filters data using a local threshold, one replica might keep all examples while another drops some. To avoid this, make control flow deterministic and perform any data-dependent filtering before distributing the data. This often means padding sequences to a fixed length or standardizing image sizes. During early debugging, log tensor shapes so you can quickly spot and correct any discrepancies before they lead to runtime errors. Python code, replica shape mismatches. This script shows how replica shape mismatches can occur when using TensorFlow's distribution strategy. It works with simple data to make it easier to see where shapes differ across replicas. The main goal is to help you identify and debug these shape inconsistencies when running distributed computations. The line starting with an exclamation mark is a shell command that installs TensorFlow version 2.20.0. Using this exact version makes sure the script runs with the expected library behavior. This is important for compatibility, since features can change between versions. It also supports reproducibility, so others can run the same code and get consistent results. We begin by importing several key modules that the script needs: The operating system module lets the program interact with the computer's operating system. The random module is used to generate random numbers, which can help with tasks like shuffling data. We then import NumPy for efficient numerical computations with large arrays and matrices. Finally, we bring in TensorFlow, a machine learning and deep learning library that we will use to build and train models. Together, these imports provide the core tools required for the script to run effectively. We start by setting a seed value, such as 42, so that any random operations give the same results every time we run the code. To achieve this, we set the seed for the random module, then for NumPy, and then for TensorFlow. Using the same seed across these libraries makes our experiments reproducible and keeps results consistent, which is especially important for debugging and comparing runs. The code first prints the TensorFlow version so you know which features and behaviors are available and can check compatibility. It then checks how many graphics processing units are detected by listing the physical devices of type GPU. This reveals the computational resources you have for running the program, which is especially important for optimizing performance in machine learning tasks. The code checks how many GPUs are available and chooses a training strategy accordingly. If multiple GPUs are present, it uses TensorFlow's mirrored distribution strategy, so the model can train on all GPUs in parallel, speeding up the process. If there is only one GPU or no GPU, it falls back to a single device strategy on the CPU. This approach lets the same code run efficiently on different hardware setups by automatically selecting an appropriate parallel processing strategy. The code reports which distribution strategy is currently in use by checking the type of the strategy object and reading its class name. This tells the user whether the model is running with a mirrored strategy across multiple graphics processors or with a single device strategy on a central processor. Knowing this helps the user understand how the model is being distributed over the available hardware resources. We start by reading how many replicas are in sync from the strategy object, which tells us how many copies of the model will run at the same time. We then choose a global batch size of 8, meaning 8 samples are processed in total during each training step across all replicas. To balance the work, we divide this global batch size by the number of replicas to get the batch size for each replica. This per-replica batch size is the number of samples each individual copy of the model processes on its own, ensuring the workload is evenly shared. This script reports how batch processing is configured across multiple devices. It first prints the number of replicas, which comes from the chosen distribution strategy. Next, it shows the global batch size, meaning the total number of samples processed in one step across all replicas. Finally, it computes and prints the per-replica batch size by dividing the global batch size by the number of replicas, indicating how many samples each replica processes. This helps ensure the workload is evenly shared across all devices. We begin by creating a small example dataset, where the number of samples is deliberately set to the global batch size plus 3, so the dataset size does not divide evenly by the batch size. This lets us illustrate how mismatched shapes can appear across different replicas during distributed training. We then generate feature data using TensorFlow's random normal function, producing a tensor with the chosen number of samples and 4 features per sample. In the same way, we generate label data with 1 label per sample. This setup allows us to study how these uneven shapes influence the behavior of distributed training. We start by creating a dataset from the input features and labels using TensorFlow's method that builds a dataset from tensor slices, which prepares the data for batching. We then batch this dataset using a chosen global batch size and set the option to not drop the remainder. As a result, if the total number of samples is not an exact multiple of the batch size, the final batch will be smaller. During distributed training, this smaller last batch can lead to shape mismatches across different replicas. We first turn our feature and label data into a TensorFlow dataset using the method that creates datasets from tensor slices, which prepares the data for TensorFlow operations. We then batch this dataset using a chosen global batch size and enable the option that drops any incomplete final batch. Dropping the remainder ensures that every batch has the same shape, which is important when training across multiple replicas. This consistent batch shape helps prevent shape mismatches when using distribution strategies. We start by distributing the dataset that was created without dropping the remainder of the batch across all available devices using the strategy's experimental dataset distribution method, so it can be processed in parallel on multiple replicas. This enables efficient training in a distributed environment. We then distribute the second dataset, which was created with the remainder dropped, so that all replicas receive batches of consistent size. Ensuring consistent batch sizes is important because it prevents shape mismatches during training and keeps the data aligned with the requirements of the distribution strategy. Within the strategy scope, we build a simple Keras model that takes 4 input features, passes them through a dense layer with 4 units and a ReLU activation to add nonlinearity, and then through a final dense layer with 1 unit to produce the prediction. We use stochastic gradient descent as the optimizer with a learning rate of 0.01 to update the model's weights during training. The loss function is mean squared error with no reduction, so it computes a separate loss value for each example. This consistent model, optimizer, and loss setup is important to ensure all replicas behave the same during distributed training. We define a single training step as a TensorFlow function to make execution more efficient. Within this step, we unpack each batch into input and target data, then use a gradient tape to record operations for automatic differentiation. The model processes the inputs in training mode to produce predictions, and we compute the loss for each example by comparing these predictions to the true targets, then average the loss over the batch. Using the recorded operations, we calculate gradients of this loss with respect to the model's trainable variables and apply them with the optimizer to update the model. The function finally returns the average loss and the number of examples processed in that batch. The training step starts by running a step function on all replicas using the distribution strategy. This function processes the distributed inputs and produces a loss value for each replica. The code then uses the strategy to average these losses across replicas, giving a mean loss. It also sums the batch sizes from each replica to get the total batch size. Finally, it returns the mean loss and the total size as a summary of the training step. The inspect batch function is used to check the shapes of data batches that have been split across different replicas. It prints a message indicating which batch is being inspected, using a label you provide. This helps with debugging and understanding how the data is divided among devices in a distributed training setup. Inside this function, the input data is split into 2 parts, 1 batch for the features and 1 batch for the labels, so each replica has its own set of inputs and targets. The function then prints the shape of the feature batch to show the dimensions of the current input data. It also prints the shape of the label batch to show the dimensions of the corresponding labels. Finally, it returns 0 as a placeholder, since the main purpose of the function is simply to display these shapes for debugging. The strategy's run method is called with the show function and the distributed batch, so that the show function runs on every replica in the strategy. This lets us inspect the shape of the data on each replica at the same time. The returned value is ignored because we only care about the side effect of printing the shapes, not about any output from the function itself. We iterate over the distributed dataset that was created without dropping the remainder, so batch sizes may differ across replicas. From this dataset, we take only the first batch and pass it to an inspection function, along with a label indicating that it comes from a dataset without dropped remainder. The inspection function prints the shapes of the data on each replica so we can see how the data is distributed and detect any mismatched shapes. After inspecting this initial batch, we stop the loop because our only goal is to examine that first batch. We iterate over the distributed dataset labeled as good, which is set up to drop any leftover batches so that all replicas receive batches of the same size. From this dataset, we take only the first batch and pass it to a batch inspection function. That function prints the data shapes for each replica so we can confirm that the batch sizes match our expectations. Once this first batch is inspected, we stop the loop since our only goal is to verify the batch configuration. We now run a single training step using the previously defined function on a dataset batch prepared with the drop remainder option so that all replicas receive batches of the same size. This avoids shape mismatches during distributed training. The function returns the loss value and the number of examples processed in that step. We print the loss as a floating point number to monitor how well the model is learning. And we print the number of examples as an integer to confirm that the batch was processed correctly. This script shows how to handle replica shape mismatches when using TensorFlow's distribution strategy. It sets a reproducible environment, selects an appropriate strategy based on available GPUs, and builds a dataset whose batch size does not evenly divide the number of samples, which can cause inconsistent shapes across replicas. To address this, it compares a dataset that keeps the leftover batch with one that drops the remainder, revealing how dropping the remainder avoids shape mismatches. A simple neural network and distributed training step are then defined within the strategy scope, and training is run on the corrected dataset. The example emphasizes that ensuring consistent batch sizes across replicas is crucial to prevent errors during distributed training. Managing local variables. When moving from single device to distributed training, it is important to distinguish between local and global variables. Local variables have separate values on each worker and are useful for things like batch counters or temporary statistics. However, if they are not managed carefully, they can lead to inconsistent metrics or errors across workers. In contrast, global variables share a single value across all workers, so confusing the two types can result in unstable training behavior. In distributed training, you must carefully control where local variables are created and how they are updated. Variables defined inside the distribution strategy scope are usually mirrored across devices, while those defined outside may live on only one device. Local variables such as metric variables are often created separately on each replica and then aggregated. If you accidentally create a variable inside a per-replica function when it should be shared, you can end up with unsynchronized copies, errors, memory leaks, and inconsistent values. To avoid this, define such variables once in the correct scope, instead of recreating them each time they are used. When debugging distributed training, you need to clearly distinguish which variables are local to each worker and which are shared across workers. If logs or metrics differ between workers, it may mean local and global variables are mixed up. Check where variables are created, make sure metrics are defined only once, and confirm that per-replica states such as random seeds are handled correctly. Mismanaged variables can lead to inconsistent loss values or stalled training, especially if the optimizer state is not shared properly. By carefully tracing how variables are created and updated, you can find these issues and keep distributed training stable. Python code, managing local variables. This material explains how to manage local variables while working with TensorFlow distribution strategies. It emphasizes using these strategies in a safe way so that variables are created and used correctly across different devices. The main goal is to help you identify and debug problems related to where variables are placed in a distributed setup. By understanding this, you can avoid common errors and ensure your distributed TensorFlow code runs as intended. The commented line is a reminder to install TensorFlow version 2.20 if it is not already available in your environment. It is optional and only needs to be run when the required version is missing. This precaution helps ensure the script runs smoothly without dependency errors. It also makes sure a specific TensorFlow version is used, reducing the risk of conflicts with other installed versions. The script begins by importing 3 key libraries to prepare for data handling and computation. It imports the operating system library to work with things like file paths and environment settings. It then imports the random module to generate random numbers for tasks such as shuffling or seeding. Finally, it imports the numerical computing library NumPy to efficiently work with arrays and perform mathematical operations. Together, these imports set up a basic environment for managing data and running numerical calculations. We begin by importing TensorFlow, a library used for machine learning and deep learning, so we can build and train models. From TensorFlow, we also import Keras, which offers a simpler, high-level way to define and train neural networks with less code. With these imports in place, we are prepared to use TensorFlow's distribution strategies to manage computations efficiently across multiple devices. We set a seed value, such as 42, so that all random operations become reproducible. This seed is applied both to the standard random library and to NumPy's random number generator. Using the same seed in both places ensures that the same random numbers are produced each time the code runs. As a result, experiments can be repeated reliably, and debugging becomes easier because the randomness is controlled and predictable. We set the TensorFlow random seed to a fixed value, so that any random operations it performs are reproducible. This means TensorFlow will generate the same sequence of random numbers every time the code runs. As a result, experiments become consistent across runs, which is essential for debugging and for reliably comparing results. This command displays the version of TensorFlow currently in use. It provides a quick check that your environment is running the intended TensorFlow version. Confirming the version is important to ensure compatibility with your code and to help with debugging when issues arise. We use TensorFlow's MirroredStrategy to control how computations are distributed across multiple devices. This strategy replicates the model on all available GPUs and is designed for synchronous training. Each device processes a different batch of data at the same time, and their gradients are then averaged. By doing this, we make better use of hardware resources and speed up training through parallelism. To quickly create data for training, we first generate random input features using a normal distribution, forming an array with 64 examples and 4 features each. We then convert this feature array to the float32 data type, so it works smoothly with TensorFlow. Next, we generate random labels using integers that are either 0 or 1, giving us 64 binary classification targets. These labels are also converted to float32 to keep the data types consistent during training. We start by printing the shape of the features array to confirm it has the expected dimensions before building the dataset. Then we print the shape of the labels array to check that it matches the features. Verifying that these shapes align is essential, because any mismatch would cause problems and reduce the accuracy of the model during training. We begin by choosing a batch size of 8, which controls how many training samples are processed together at one time. Then we build a TensorFlow dataset from the feature and label arrays using a method that slices them into individual samples. This prepares the data in a structured way so it can be efficiently fed through the rest of the training pipeline. The dataset is first shuffled using a buffer of 64 items and a fixed seed so that the order is randomized but reproducible. This random mixing helps the model train more effectively. After shuffling, the data is split into batches of 8 samples based on the chosen batch size. Processing data in these small batches makes training more efficient and manageable, especially for large datasets. The code uses the chosen distribution strategy to split the dataset across multiple devices or replicas. This allows different parts of the data to be processed in parallel. By giving each replica its own portion of the dataset, training can run more efficiently. This parallel processing is essential for speeding up work in a distributed environment. We define a function that builds a simple neural network using Keras. It creates a sequential model with an input that expects 4 features, followed by a dense layer with 4 units using a ReLU activation to add nonlinearity. The final layer is another dense layer with 1 unit and a sigmoid activation, which is appropriate for binary classification. This structure allows the model to learn patterns from the input data and produce a prediction between 0 and 1. The model is compiled using a simple optimizer, specifically stochastic gradient descent with a learning rate of 0.1. It uses binary cross-entropy as the loss function, which is appropriate for binary classification problems. The model also tracks accuracy as a performance metric during training. After these settings are applied, the model is ready to be trained. Within the strategy scope, we build the model so that all variables are correctly placed across the available devices. This is especially important when using distribution strategies, because it helps manage resources efficiently and prevents problems with where variables are stored. By creating the model inside this scope, its variables are automatically mirrored on all devices. This allows training and updates to stay synchronized across the entire distributed setup. Within the strategy scope, we define a training loss metric using the Keras mean metric to track the average loss during training. Placing it inside the strategy scope ensures it is correctly managed when using distribution strategies across multiple devices. This way, we keep a single shared metric that aggregates results from all replicas instead of creating separate metrics for each device. We print the type of the variable behind the training loss metric to confirm that it is a mirrored variable. This special TensorFlow variable type is used with distribution strategies. By checking its type, we verify that the metric is properly configured to operate across multiple devices. This confirmation is important to ensure that distributed training works correctly. We use Keras's binary cross-entropy loss to measure how different the model's predicted binary outputs are from the true labels. By setting the reduction mode to none, we compute a separate loss value for each example instead of automatically averaging or summing them over the batch. This per-example loss makes it easier to control how losses are combined later, which is especially useful when training with distributed strategies that need custom aggregation across multiple replicas. This function computes the loss for each replica in a distributed training setup by first calculating a loss value for every individual example. It uses a predefined loss object based on binary cross-entropy applied to the predicted and true labels. The loss is computed without any reduction at this stage, so each example keeps its own loss value. This design allows more flexible and precise control over how the losses are later combined during training. The code scales the loss by the global batch size using TensorFlow's compute average loss function. It takes the loss for each example and divides it by the total number of examples in the batch. This produces an average loss that is consistent regardless of how large the batch is. This is especially important in distributed training, where batch sizes can differ across replicas, but you still want a single, comparable measure of loss. Within the strategy scope, we create an optimizer using Keras stochastic gradient descent with a learning rate of 0.1. Doing this inside the strategy scope makes sure the optimizer is placed on the correct devices. This placement is important when using distribution strategies so that resources are managed efficiently across multiple replicas. We define a training step function and optimize it with TensorFlow's function decorator for better performance. Inside this training step, we create an inner step function that unpacks the distributed inputs from each batch. This inner function separates features from labels, so the data is correctly organized. This structure is essential for parallel training across multiple devices, ensuring each replica receives the right portion of data. We use TensorFlow's gradient tape as a context that records operations so we can perform automatic differentiation. Within this context, we pass the batch of features through the model in training mode to generate predictions. We then compute the loss by calling the loss function with the true labels in these predictions. This recorded setup lets us later compute gradients, which are needed to update the model's weights during training. During training, we first use TensorFlow's gradient tracking to compute how the loss changes with respect to each trainable parameter in the model. These gradients show how each parameter influences the loss. We then pass the gradients to the optimizer, which updates the model's weights. This update step reduces the loss and allows the model to learn from the data. This part of the code updates the global training loss metric, doing so once for each replica in the distributed setup. By updating the metric for every replica, it accurately tracks the loss across all parallel computations. The function then returns the computed loss value so it can be used for further processing or logging. This ensures a consistent and reliable view of training progress throughout the distributed system. The strategy uses its run method to execute the step function on each replica at the same time. It sends the distributed input data to these replicas as arguments to the step function. This way, each replica handles only part of the data. Running these parts in parallel makes training much more efficient in a distributed environment. This code uses TensorFlow's distribution strategy to combine loss values from all replicas. It calls the strategy's reduce function with a sum operation, so it adds together the losses computed on each replica. The axis is set to none, which means the reduction is performed across all dimensions. The result is a single scalar value that represents the overall loss across all replicas. We run a short custom training loop for 2 epochs, and at the start of each epoch, we reset the training loss metric. Resetting it ensures that loss values from earlier epochs do not carry over. This way, the mean loss we compute reflects only the performance within the current epoch. As a result, we can accurately track and compare the training loss for each epoch. In this part of the code, we iterate over each batch from the distributed dataset and call the training step function with the current batch as input. That function performs the core training work for the batch, including computing the loss and updating the model's weights. The loss value it returns is stored for that batch. This process is repeated for all batches, so the model is trained on the entire dataset. The code prints a brief summary for each training epoch by first stating the word epoch and the current epoch number. It then computes the average loss for that epoch by converting the training loss metric to a floating point value. This gives a clear snapshot of the model's performance after each epoch and helps monitor training progress over time. This script shows how to manage local variables when using TensorFlow distribution strategies. It first fixes random seeds for reproducibility and sets up a mirrored strategy to run training across multiple devices. A small synthetic dataset is created, shuffled, batched, and then distributed. And a simple sequential model with dense layers is defined and compiled within the strategy scope, so variables are placed correctly. A custom training loop runs for 2 epochs, where each batch is used to compute predictions, calculate loss, apply gradients, and update a distributed training loss metric that is averaged across replicas. Throughout the run, the script prints the TensorFlow version, dataset shape, metric variable type, and the mean loss after each epoch to illustrate how training and variable management behave under the distribution strategy. Monitoring distributed training. Monitoring distributed training is not just about watching loss or accuracy. It is about making sure every replica is healthy and resources are used well. If you only track a single overall metric, you can miss problems like a slow worker or a GPU running out of memory. Effective monitoring combines global signals such as loss and accuracy with per-replica information like step time and memory usage. By integrating this monitoring into the training loop, you can detect bottlenecks early and avoid failures or degraded model quality. In distributed training, it is important to make the behavior of each replica visible instead of relying only on aggregated metrics. Aggregation can hide problems, such as a single worker producing outlier values or lagging behind. To avoid this, track both overall metrics and per-replica metrics like throughput and error counts. By logging and visualizing these over time, you can better understand how replicas coordinate and detect issues such as network delays, shape mismatches, or incorrect variable placement. Monitoring is crucial for diagnosing sporadic errors in distributed training, especially under full load, such as shape mismatches or variable placement problems caused by memory pressure. Detailed logging of key operations, including dataset iteration and replica synchronization, helps reveal when and where these issues occur. In cases like recommendation systems, some errors may only appear for certain data samples, making logs and monitoring tools essential for pinpointing the cause. By combining systematic logging with metric dashboards, you can turn seemingly random failures into recognizable patterns that are much easier to trace and fix. Python code, monitoring distributed training. This script demonstrates basic distributed monitoring using a mirrored strategy and simple metrics. Its main goal is to show how to track model behavior across multiple devices in a straightforward way. The focus is on safe, concise debugging practices rather than complex features. Overall, it provides a minimal example of how to monitor distributed training effectively. The line that begins with an exclamation mark is a command to install TensorFlow version 2.20.0. It is commonly used in environments such as Jupyter Notebooks to make sure that this exact version is available. Doing this helps ensure that the code that follows runs correctly and remains compatible with the specific features and behavior of that TensorFlow version. We begin by importing a few standard Python libraries needed for the script. The operating system library lets us work with things like file paths and environment settings. The random library provides tools for generating random numbers, which can be useful for setting seeds or creating random data. Finally, we import NumPy, a numerical computing library that helps us efficiently create and manipulate arrays and perform mathematical operations. We begin by importing TensorFlow, since it is the main library used to build and train our machine learning models. Right after importing it, we check which version is installed. This matters because different TensorFlow versions can change how certain features work. Confirming the version helps ensure that our code runs correctly and remains compatible with the rest of the project. We begin by setting a seed value of 42 so that any random operations in our program become reproducible. Using the random module, we apply the seed to Python's built-in random number generator. This makes sure that each time we run the code, we get the same random results. Consistent results are especially important when debugging or comparing different runs of an experiment. We set the random seed for both NumPy and TensorFlow so that any random numbers they generate are the same every time the code runs. This makes our experiments reproducible and helps with debugging, because results will not change unpredictably between runs. In TensorFlow, this includes random operations like initializing neural network weights. By fixing these seeds, we ensure consistent behavior across runs, which is essential for reliable testing and comparison of results. This line checks and prints the version of TensorFlow currently in use. It helps you confirm that the correct version is installed and running. This is important because different versions may support different features or functions. Verifying the version ensures your code is compatible with the TensorFlow environment. The code first checks whether any GPU devices are available through TensorFlow. If GPUs are found, it uses a mirrored strategy, so the model can be copied across multiple GPUs for distributed training. If no GPUs are detected, it falls back to a single device strategy on the CPU. This setup lets the training automatically use the best available hardware, while still running correctly without GPU support. This code reports how many replicas are currently in sync under the selected distribution strategy. It lets you quickly see how many devices are actually being used for parallel processing. This information helps you understand the effective scale of your distributed training setup and confirm that your resources are being utilized as expected. We begin by creating a small synthetic dataset with 256 samples. Using a random number generator, we produce features arranged in a table with 256 rows and 8 columns, where each entry is a random value. These values are stored in 32-bit floating point format to keep them consistent and compatible with later TensorFlow operations. We create binary labels from our feature data by first summing the values in each row, then checking whether each sum is greater than 0. This check produces a set of true or false values, where true means the row's sum is positive and false means it is not. We then convert these Boolean values into floating point numbers, with true becoming 1.0 and false becoming 0.0. This gives us numeric labels suitable for binary classification tasks. Before building the dataset, the code checks that the number of feature samples matches the number of labels. This ensures every feature vector has a corresponding label, which is essential for correct model training. By enforcing this condition, the code avoids problems like mismatched data sizes that could cause runtime errors or lead to an incorrectly trained model. We start by setting the batch size for each replica to 8, meaning each replica processes 8 samples at a time. The global batch size is then found by multiplying this per-replica batch size by the number of replicas working in sync. This calculation ensures that the total workload is evenly split across all replicas. Having an even distribution of the batch in this way is important for efficient parallel processing and distributed training. We begin by turning the feature and label arrays into a TensorFlow dataset using the method that creates a dataset from tensor slices, which lets TensorFlow handle the data efficiently. We then shuffle this dataset so the samples are mixed in a random order, helping to reduce bias during training. The shuffle operation uses a buffer size equal to the number of samples and a fixed seed value so that the random shuffling can be reproduced in future runs. The code prepares the dataset by batching it with a global batch size that matches the number of replicas in the distributed strategy, so each replica receives an equal share of data. After batching, the dataset is set to repeat 3 times, which means the model goes through the same data multiple times during training. This repetition improves training stability and helps the model learn more effectively from the available data. The code uses the selected strategy to split the dataset across all available devices so they can process data in parallel. Each replica receives its own portion of the dataset, allowing the workload to be shared. This distribution is essential for efficient distributed training because it makes better use of hardware resources and speeds up the overall training process. We define a function that builds a simple neural network using the Keras sequential API in TensorFlow. Pause. The network takes input data with 8 features, then passes it through a dense layer with 16 units that uses the ReLU activation to add nonlinearity. Pause. It then outputs through a final dense layer with 1 unit and a sigmoid activation, making it suitable for binary classification. Pause. The function returns this model ready to be trained on labeled data. Within the strategy scope, we first build the model using the previously defined function so it is compatible with distributed training. We then create an atom optimizer with a learning rate of 0.01. This optimizer updates the model's weights during training to reduce the loss function and improve performance. Within the strategy scope, we define a binary cross-entropy loss in TensorFlow that expects probability inputs rather than raw logits. We set the reduction mode to none, so the loss is computed separately for each example instead of being combined into a single value automatically. This gives us finer control over how we later aggregate the loss, which is especially helpful in distributed training, when we may want to manually average the loss across multiple replicas. This function computes the loss for each replica during distributed training. It first calculates the binary cross-entropy loss for each example, then reshapes the result into a one-dimensional tensor for consistent processing. After that, it averages the loss across all examples, taking the global batch size into account. This averaging keeps the loss scale consistent across different numbers of replicas, which helps maintain stable and comparable training behavior under various distribution strategies. As part of our training strategy, we define metrics to monitor how well the model is learning. We use TensorFlow's mean metric to track the average training loss over time, summarizing how far predictions are from the true values. We also use a binary accuracy metric to measure how often the model's predictions match the correct binary labels. Together, these metrics provide a clear view of the model's performance during training. The training function starts by splitting the input into features and labels, and uses TensorFlow checks to confirm that the features have 8 columns and that the labels have a matching number of rows. Within a gradient tracking context, the model generates predictions on the features in training mode, and these predictions are squeezed to remove extra dimensions. A custom loss function then computes the loss from the labels and predictions, and the gradients of this loss with respect to the model's trainable variables are calculated. The optimizer applies these gradients to update the model's weights, and the training loss and accuracy metrics are updated based on the current loss and predictions. Finally, the function returns the computed loss value. We define a distributed training step as a TensorFlow function to optimize execution. Then use the distribution strategy to run the train step in parallel on all replicas with the given inputs. This produces a separate loss value from each replica. We then use the strategy's reduction method to combine these losses into a single mean value across all replicas. The result is one average loss that represents performance across all devices. We run a short distributed training loop that tracks both performance and timing. The loop processes batches from the dataset, but stops after at most 5 steps. For each step, we record the start time, run the distributed training step on the current batch to get the mean loss, then record the end time and store how long the step took. Every 2 steps, we log the current step number along with the average loss and accuracy so far. This setup lets us monitor training progress while also measuring how long each step requires. The training code measures performance by computing the average time per step. It adds up all recorded step times, then divides by the total number of steps to find how long a typical step takes. This average step time is then printed, rounded to 4 decimal places, giving a clear and concise metric for evaluating the speed of the training loop. This script shows a simple setup for monitoring distributed training in TensorFlow using MirroredStrategy. It first fixes random seeds for reproducibility and checks for available GPUs, using multiple GPUs when possible and falling back to a single CPU otherwise. It then builds a small synthetic dataset with binary labels and defines a basic neural network with 2 dense layers, trained with the atom optimizer and binary cross-entropy loss. During training, the work is distributed across replicas, and the script tracks loss and accuracy while also measuring the average time per training step. Overall, it provides a compact example of how to configure, run, and monitor distributed training with a focus on reproducible and efficient use of hardware resources. In this lecture, you learned to configure and run model.fit under a tf.distribute strategy for multi-GPU or multi-worker setups. Implement a custom training loop that uses strategy.run and distributed datasets. And troubleshoot common distributed training errors related to shapes, batch sizes, and variable placement. In the next module, Module 9, we will go over production and serving.
Thank you for your attention. See you all in the next lecture.